Hello everyone, welcome to Chemazon-Complete Chemistry. So in our today's video, we are going to learn a very important topic of stereochemistry that is called as topicity. So in this video, we are going to understand terms like what is homotopic, heterotopic. In heterotopic also there are different types, that is constitutionally heterotopic, stereochemically heterotopic, enantiotopic and diastereotopic. This is one of the examples that we are going to see. So let us first understand what exactly is topicity. So if you see the word topos, topos is a Greek word which means place. So what exactly is the meaning of topicity? Topicity is nothing but we study the stereochemical relationship. Stereochemical. It is the stereochemical relationship between two groups or ligands in a particular molecule. Between two groups or ligands of a particular molecule. Okay, whether they are same or whether they are different, what is the stereochemical relationship that we are going to see in detail. Now the question is why exactly we are going to find the topicity, what are its applications. So first application is to study the biochemical reaction. Okay, to finding out the stereochemical relationship is important to study biochemical reactions or reactions that occur naturally, biochemical reactions. This is one of the applications. Another application is to predict the it will be useful. This knowing the stereochemical relationship between two groups or ligands, it will be helpful to predict the number of signals and splitting pattern. Okay, number of signals, okay, and the splitting pattern in NMR. In NMR we use this concept of two groups to be stereochemically equivalent or non-equivalent. What is the relation between them? Okay, that we are going to see in NMR, nuclear magnetic resonance. There it is important to know whether a set of groups are whether they are same or whether they are different. Okay, so let us first understand what are the steps to finding out the topicity. So first step is what you are going to do is replace. Okay, suppose I will take some molecule. Let's say this molecule I take, and there are two groups for which I want to find out the stereochemical relationship. Let's say HA and HB. This molecule we are going to see again. Suppose I want to find out the stereochemical relationship between these two hydrogens. So what I'm going to do is replace one by one both the groups, okay, whose relation you want to find out, stereochemical relation you have to find out. Replace one by one both the groups with some other atom. Okay, with some other atom. What does this exactly mean? Suppose first what we have to do, replace, let's say, HA with some other atom. Let's say I replace it with its isotope D. CH3, I'll replace HA with D. I'll keep HB as same. And next what I can do, I will change the other molecule HB with, I will replace other ligand with the same atom that I had replaced for the first one. So CH3, C, HA, now it will remain same. Instead of HB, now there is deuterium. Okay, so this is the first step. Okay, replacement is done. What is the next step? Next step is you have to find out the relationship. Okay, stereochemical relationship between the two molecules after replacement. Stereochemical relationship. You have to find out the stereochemical relationship between the two molecules. Okay, this we had seen so many times. What is the meaning of stereochemical relationship? You have to find out whether these two molecules that we had formed after replacement, between the molecules after replacement. Okay, after the replacement, whether the two molecules are identical. Okay, identical or same, whether they are constitutional isomers, okay, whether they are enantiomers, whether they are diastereomers, okay, whether they are enantiomers or they are diastereomers. Okay, so all those big names that you saw in the first slide, that is nothing but based on the stereochemical relationship between the molecules after replacement. It's very simple, we'll see in a minute. Okay, so classification. So after replacement, okay, there are two types basic, they are of two types, homotopic and heterotopic. Okay, if you get the same molecules, okay, if you get the molecules that are there after replacement, if they are same or if they are identical, then we say that the two groups or ligands, they are what? They are homotopic. Homo means same. Okay, they are same place. Same place. Topic means place. Homo means same. So same place. Same place means they have same stereochemical relationship. So they we call them as homotopic. Now heterotopic, what we have to do is we will see heterotopic means hetero means different. Okay, they are of different place. They have different stereochemical relationship. Okay, and they are also of different types. We'll see in a moment. Heterotopic, how we will find out, let us see that in a moment. Before that, let us understand how do you find out whether two groups are homotopic. So this is an example of a homotopic group. So first what I will do, I will replace, I have to find out the relation between HA and HB. So I will replace HA with, okay, this is the same step that we had done for finding out pro R and pro S. If you had seen that video, you would remember that this is the same step that we had repeated in finding out the notation pro R and pro S. Okay, so first replacing HA with some group, let's say Cl. Okay, so what I will get, CH3, C, CH3, HA I am replacing it with Cl, and HB I am keeping as it is. Okay, next step is replacing HB with Cl. Okay, CH3, C, CH3. Now HA will remain as it is. HB I am replacing it with Cl. So now you have to tell me what is the relation between these two molecules. So the first molecule, if you see, is it chiral? No, because there are two same groups attached to the carbon. So there is no chiral center. So what will happen is, if what I do, if I rotate this molecule, okay, if I rotate this molecule out of plane by 180 degree, okay, I invert the molecule or I flip the molecules, what I will get is, I will get the same compound, the second one. Okay, what I will get, this Cl will come on the right and this HB will go on the left. Okay, so H, and here there is Cl. So you can see both these are what? They are same. So both these molecules are what? They are identical. Okay, if they are identical or same, what is the relationship between the two ligands or groups? They are what? They are homotopic. They are homotopic. Okay, so this was the example of homotopic ligands. Now, how do you find out for the different types of heterotopic ligands that we are going to see now? So first, for finding out the heterotopic ligands, what you have to do is you have to check the position of the groups. Position of the groups. Okay, if they are at the, if the groups, let's say two hydrogens, HA and HB, if HA and HB, they are present at the same, at the different carbon, let's say. Okay, they are present at the different carbon. And the second case is if HA and HB, they are present at the same carbon, okay, same carbon or same position. If they are present at the different carbon, what we are going to get is the relation between them will be what? They will be constitutional isomers. Okay, what is the meaning of constitutional isomers? The bond connectivity is different. For example, position isomers. Okay, what are position isomers? Functional position of the functional group is different. What are constitutional isomers that we had seen previously? Bond connectivity is different. Okay, if they are constitutional isomers, that is a position of the groups is different, that both HA and HB are attached to different carbons, then we call those HA and HB as constitutionally heterotopic. Okay, constitutionally means they in a constitution they are constitutional isomers. That is why we say they are constitutionally heterotopic. Okay, next is if HA and HB are present at the same carbon. Here they can be of two types. One is they can either be diastereomers. Okay, the relation between them can be diastereomers, or it can be enantiomers. Okay, and what are these diastereomers and enantiomers? In general, what do we call them? We call them as stereoisomers. Right, they are stereoisomers. That is the reason why if the HA and HB they are present at the same carbon, but they are different molecules. Okay, same carbon, same molecules, it will become homotopic. But same carbon and they are different molecules. Okay, they are either diastereomers or enantiomers. Then we call them as stereochemically heterotopic. Okay, now let us understand this with the help of examples. First is constitutionally heterotopic. Now here I have to find out the relation between HA and HB. Again I will do the same thing. Suppose now this time I replace HA by chlorine, let's say. What I will get? CH3, CH, Cl, CH2 and HB. HB I will keep as it is. Next what I am going to do, I will replace HB by Cl. Okay, CH3, CH, HA I will keep as it is. CH2, Cl. So if you see here, this is what? 1, 2, 3. 2 chloropropane. Okay, 3 carbon means propane. 2 chloropropane. And here if you see 1, 2, 3. This is 1 chloropropane. That is the position of the halogen is different. Okay, position of the halogen is different. That is why they are what? They are position isomers. Okay, position isomers, and we know what are position isomers. They are a type of constitutional isomer. What are the different types of constitutional isomers? In the isomerism video we had seen, they can be position isomers if the position of the functional group is different. If the functional group itself is different, then we call them as what? We call them as functional isomers. Okay, they can be any constitutional isomer, functional isomer. Okay, here there is position isomers. They are constitutional isomers. That is why we call HA and HB here. They are what? They are constitutionally heterotopic. Constitutionally heterotopic. Okay, next is stereochemically heterotopic. We had seen just now, if the relation between the two molecules is enantiomers, then we call them as enantiotopic. Okay, then the two groups or ligands, they are called as enantiotopic. And if they are what? They are diastereomers. Okay, then we call them as diastereotopic. Now let us see their examples. Enantiotopic, again what I will do, I will replace one by one HA with chlorine, some other atom. Let's say here I am replacing with chlorine. Okay, CH3 OH. Suppose now I show the stereochemistry. Let's say below the plane I have HA is replaced by Cl, and above the plane HB will remain as it is. So now you can see this is a chiral center. So for a chiral center, what we can do, we can find out their absolute configuration. So let us do that. Primary atom is oxygen, carbon, chlorine and hydrogen. Which has the highest atomic number? Chlorine. So it will get the first priority. Then there is oxygen. Oxygen atomic Number is 8. So this will get second priority. Carbon is 6. So it will get third priority. This will be 4. Now 1, 2, 2, 2, 3. It is what? It is clockwise. Clockwise, but the fourth priority group is on the wedge bond. Okay, clockwise it should be R. But since the fourth priority group is on the wedge bond, this will become what? This will become S. Okay, similarly what we can do for the other atom HB, replacing now HB with Cl. CH3, OH. Now below the plane there is hydrogen, HA will remain as it is, and above the plane what I am doing is, above the plane we have Cl. So again we'll do the same thing, we'll assign the numbering 1, oxygen 2, carbon 3, hydrogen 4. So 1, 2, 2, 2, 3. Now it is what? Now it is again it is clockwise, but the fourth priority group is on the dash bond. So the absolute configuration will remain R. One is S, another is R. They are what? They are enantiomers. Okay, since they are enantiomers, the relation between HA and HB is what? Enantiotopic. Okay, and the last one is diastereotopic. Now, what is the best way to identify diastereotopic? Already there will be one chiral center that is present. Okay, if it is an alkane or a straight chain compound, there will be already one chiral carbon that is already present before replacement. So after replacement, what we will get is CH3C. Now let's say I replace HA with D. Okay, or let's say again I replace it with Cl. Cl, below the plane there is Cl, and above the plane there is HB, CH3C, CH3, other carbon it will remain as it is, OH. Okay, above the plane I have Br. Okay, now replacing HB with Cl. Carbon CH3. Now below the plane HA is as it is. HB we are replacing it with Cl. Below the plane OH. Above the plane Br. Okay, so here you can see that this chiral center, the stereochemistry is same. OH is below the plane, Br is above the plane. But other chiral center, you can see here Cl and H, both their positions are interchanged. So if we change the stereochemistry at only one of the chiral carbons, what they are called as? They are called as diastereomers. Okay, they are called as what? They are called as diastereomers. Okay, hence these are what? These are called as diastereotopic. Okay, where else we can see diastereomers in cis trans isomer, right? Suppose I take a alkene CH3 Cl HA HB. Okay, so I'll draw the same molecule, and then what we will do, we will replace them with some other group, and then we will see their relationship. Suppose I replace HA with Br, and second molecule I replace HB with Br. Okay, here also we can see their diastereomers. We can assign what? We can assign EZ nomenclature here. So we can, how do you find out EZ? First assign the priority. Bromine and hydrogen, which has higher atomic number, 1. Okay, hydrogen has lower, so it will be second priority. Okay, between carbon and chlorine, which has higher atomic number, chlorine, so 1 and 2. So you can see the higher priority groups, they are on the opposite side, so it will be E. Okay, I told you one trick how to remember egg open. That means if the groups are on the opposite side, higher priority groups are on the opposite side, it will be E. Okay, higher priority groups on the opposite side, O for opposite. Okay, this was a trick that I told you to remember. Egg open. Okay, opposite side E, and if they are on the same side, higher priority groups that is 1 are on the same side, then it is Z. Here you can see again we will give bromine 1, hydrogen 2. Here this will get 2 and chlorine will get 1. So you can see 1 1 higher priority groups are on the same side. This is which, what will be the, this will be Z. Okay, notation will be Z. This is E and Z. They are what? They are diastereomers. So in alkenes also we can see what? We can see they are what? They are diastereotopic. Okay, so this is the end of the video. I hope you have understood all the different terminologies: homotopic, heterotopic, constitutionally heterotopic, stereochemically heterotopic, enantiotopic, and diastereotopic. Only the names are big. Their meaning is very simple, and I hope you have understood all the examples. This is a very, very important topic. Thank you.